and then I need to multiply times seconds to get the cubic meter, and then I have to displace the volume along the y. Here, there is something that can be improved. Because actually, if the shoreline is tilted in this way, in order to compute the advance of the shoreline in this direction, what I need to do is to divide not by dy, which is basically this. I need to divide it by the full length of the shoreline. This is something based on my reasoning, because the code that I got from my colleague is divided by dy, but I don't think it is correct. I mean, if it would be correct if the beach is displaced along this direction, and therefore I would get the psi along x, but if the beach is displaced in this direction, it's a longer distance where we need to get the area. So basically,
we need to project the delta along the.
Yeah, but yeah, I think you know, it's not having a significant effect. But if the I mean, if you think about a situation where the shoreline is along x, it is, if you divide by the y is 0, essentially, and therefore this is not a, I think it's not a good thing. One should correct this.
Yeah, but do we know for each step the inclination?
Yeah, we know it, and it takes a bit of time, because you have to compute the angle, and you have to recompute the angle.
Because we know each step because.
Yes. Yeah, it takes a bit of time, but it's possible. But now let's move forward by just dividing by dy, okay, which is a good approximation, because keep in mind that, I mean, we are talking about formulas that have an approximation of, if we are very lucky, 30–40%. So, I mean, it's not but anyway, this is something that can be improved. Okay, and then we can write that x and c j, squares, j is equal to x and c j plus xc. And then we need a curly bracket here, a right curly bracket. And then let's write over the graph lines x and c, y, all equal blue. It should work. Let me look at the graph here. Yeah. It should work. I think I removed all the comments, so I think that we can try. Let's try. Okay, let's look at the graph. Yeah, it is basically coincident. It means that there has been a very small displacement. Let me understand why. Because, because it is, do you remember that the time step is just 1? We need to, here, I don't understand why I thought I kept This is why it didn't change anything. Okay, so let me try it again. And let's see. Yeah, this is what happened, which is a little bit concerning because it means that there is instability. So it means that the time step is too huge. So let me change the time step then. Because if I look at the forcing file, just 1 second, it's here, wave forcing. So we can try with 10 seconds. Still there is something in the results that I'm not sure it is correct, because I was expecting something more, but let's see. Yeah, now it's more reasonable, as you see.
Is it possible to see the code once again? Because I have a problem with lines.
Yeah.
Si sovrappongono le due.
No, io sono in originale.
Just 1 second. Lines?
Lines.
Yeah.
Is the unexpected input in lines?
I think there is a mistake in.
XLC?
If you look at the syntax, it should be correct.
Excuse me, the time step is the first line of wave forcing, or
The time step is, let me see.
But can we define the episode? Yes.
It's, no, the first line is the Y.
okay, because I have 3.47.
I was expecting some more stability, so I just want to give to put an eye on the code because
But why can you close twice the parentheses at the end?
because it's one closes the 4 and the other one closes the simulation over the delta t. And if you don't close them, you get an error. Because two were open, and so I'm really sure. I'm just looking for. Let me look at the data just for a second. I think it is correct. I mean, it is quite to be expected. You know, when you basically, what is that dictates erosion and deposition? It is the wave forcing. And indeed, if you look at the wave forcing, there are changes. So there are some points where you have the wave forcing that changes significantly. And therefore, I am expecting that if one takes a refined look, one would see that where there is a sudden turn from deposition to erosion, there is a change in wave forcing significant. So probably there is a wave height that is increasing and therefore causing erosion. And then the part that is eroded, you see that it's settled later on, probably when there is the wave forcing that decreases. So it is to be expected. There is to say that when you have the shoreline that is taking some, you know, strange configurations like this one, this is a bit exaggerated. I mean, when it takes some strange configuration, one needs to be to check the wave forcing, because it may be unreliable that you have these changes in the wave forcing. And it's interesting also to see that the same instabilities apply if you adopt a different equation for computing sediment transport. Now let's try to introduce another equation that I didn't explain to you. It's purely empirical, but let's try to use it. And let me write it and then I tell you so we can make a comparison. And keep in mind that when you turn from an empirical formulation to another one, you could get results that differ by an order of magnitude, because empirical relationships, you know, this is something that is to be expected. So let's go to the place here where we apply the CFC formula, and let's comment it. And then let me write QLII is equal to, this is called Campuis formula. Campuis formula. And it is the first one because he proposed several variants. This is the one of 1986. So it's equal to an empirical coefficient, which is equal to 1.28 times S, which is the slope of the beach, divided by D50, which is the diameter, the representative diameter of grains, times HB ounce to the power of 3.5 times sin 2 times alpha 1 and this is in days, so it's a rate, volumetric rate per days, so we need to divide times 86,400 and multiply it by the T. Should be correct. So again, you have an empirical coefficient here, which takes into account several features, including the density of sea wave and the density of sediments, mass density. So it could be updated with the values of densities that we adopted here, but let's keep this one, okay? Which takes basically a value for the sediment density of 2600 and a value for the sea water density of, I think, 1.025. So these are standard values. And then you have the slope of the beach, D50, and basically wave height at the breaker at the power of 3.5.
But do we have to define the D50?
Yes. And if it is not defined, we have to. And alpha 1 is the same. So we have to define S and D50. Let me see if I defined it. I don't think so. Okay, so S, let's take 1/30 and B50 M. We can take 0 points, so in this way it would be 1 millimeter. Let's use 5 half millimeter. Okay, we can try. I'm curious to see what happens. In this case, there is no change. I wonder whether I made a mistake. Let me see. Yeah, it means that there is a very small sediment transport. And I want just to check if I didn't make any mistake. It seems not. And let me put just a parenthesis here because I'm not sure. It should work anyway. It shouldn't make any change, but I just want to be sure. And okay, let me try again. I think it doesn't change anything, but I just want to make sure. Okay, they overlap, so let me then make this experiment. First of all, delta t is correct. Let me try to put one more zero here. With one more zero, it should work. But still, yeah, now you start seeing some changes. And another thing that I could make is wave forcing. Here, put the time step equal to 120. I guess that now it's, yeah, now it became unstable, like in the previous case.
So what did you change?
I changed the grain diameter and also the length of the time step. But actually, on my website, you should find, you are able to find both the code, the code with both formulas. And also there are the input files, the original input files. So actually yesterday I worked it out a little bit in order to propose a wave forcing that gives more or less the same response, and also a grain diameter that more or less should give the same response for the two formulas. Of course, it depends a lot on the grain diameter, so I had to look for it. So I'm not sure. I was expecting, even now, to find more or less the same results. Instead, this is not the case. So I'm not sure whether there are some issues that I'm missing in the code that I developed today. But I think that the concept is clear, and I invite you to make attempts with the code that I have on my website. Now you have the means for understanding what is there. The only thing that you have to correct, and I could correct it already now, is the index of the vector that I mentioned to you. So let me correct it now. So If you download it, I'm not sure I can do here. Just 1 second, and then I go to my lecture. So what I need to change here, this is the code that is uploaded. I need to change here from 1 to 19. Okay, this is changed, and then I can upload the code again.
We should do 19.
Yeah.
You go.
So basically, if you now download the code, it is correct, and you can play with it. Okay? Okay, so that's it. There is one addition that could be made to this code, but I'm not sure that we will have the time to make it because I don't want to concentrate on just one exercise. And the addition is to put the limits. So the constraint should be that if erosion gets, and this also avoids instability, it avoids the problem of up and down. If erosion gets to the limit that we fix to erosion itself, then you have to move the sediment transport to the next step. And this is an addition that is not easy to make. And this is something that you may want to consider if you want to make an additional exercise. Okay, I wish you a very nice Easter break, and we will see each other on Wednesday, next Wednesday, April 19. Yeah. Thank you.